Oh, you can't see the screen. Hang on. Let me slide over here a little bit. This is the shortest HDMI cord. Like, that's it. It's not even a foot long. It's at the back of the desk. It's great. All right. So we left off talking about linked lists here. We had some fun with our linked lists. I don't know if you had a chance to check out the book here. Again, not the biggest fond of how he goes about it just because of the inheritance. It's a great approach, a good thing to do, but when you try learning it, I find it obnoxious. So I'm avoiding it. So it's going to look a little different if you're reading his version versus my version, but they do the same thing, right? I've done more work than I needed. I copy-pasted a bunch as we went through the different versions, right? We had our singly linked list, which was great. It was really fast at adding all the time, even worst case. It never had to do any copying, so we were always O of 1. Getting to an index, though, was slow. Where when we had an array-based list or a regular Python list, you can get to index of 99 like that, because you could just read it out of that contiguous block in memory. We knew right where it was. With a linked list, we had to walk 99 directions. Okay, who's after you? 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 And then we looked at, hey, we could do like half of n, but thanks to fancy math, we throw away our coefficients, so half of n is still n. It still grows linearly in terms of the more I have in my collection here, the longer it takes. So not great yet. So the next thing we can do to solve that problem, or make it a little easier here, is to make this a positional list. With a positional list, we're going to change how people interact with our list. So they're no longer going to say, hey, just insert at this index or do this over here. We're going to give them a wrapper, a position to work with. And if they hold on to the position, they can do things very, very, very quickly, which is great for them. So it gives them more flexibility in how they're going to use the list. So the idea with the positional list, let me go find that one down here. I didn't, I plugged in, but didn't turn it on. Oh my goodness, I'm getting there. Let's see, circular lists, doubly linked lists. He doesn't use the dummy header node either. He still uses header and trailer. I don't like that. The circular is much better. Here we go, positional. So with a position, the idea here is you can get the element or the data stored in that position. So we're actually going to be returning positions to people interacting with our list directly. And from there, they can go get that element back out. They can get the first position or the last position. So someone interacting with our linked list will give them access to, here's where the front is, here's where the back is. Here's a position that they can use and hold on to. And then we'll say, hey, if you want to know what comes before, if you want to walk back one, I'll give you the position before this one. If you want the position after a position, I'll give you the position after. So they can do the navigation, right? So we're kind of exposing some of those details. Now, they don't need to know we're doing it with a linked list, but you could actually make a positional list with an array-based list. It'd be silly, though, because you already have index access. You don't need any of that. It doesn't gain you anything. But using positions now lets us do things like, hey, I want to add before a position. I want to add after a position. I want to replace the data at a position. I want to delete a position. So while they're interacting with our list here, we've got 1,000 things in the list. They could go find, position number 27. Because somehow that's where they are. And then at 27, they can insert into the list before and after in constant time. Remember, there's no resizing that ever has to happen. So if you have a position, you can do your inserts, you can do your removes, you can do your replaces in constant time. Nothing has to shift. Versus our array-based lists, if you wanted to delete or pop something out at an index, everything had to fill back into that spot. So it was an O of n operation. Right? The bigger my list is, the longer it takes to take something out of the middle or add to the middle of a array-based list or a regular list. With a positional list, if we can get to that position, which still takes n time to get there, once we're there, it's instant to do adds and removes. So that's the big benefit here. So if we're dealing with some sort of data that we're going to be adding and taking out of a lot here in a list, and the order matters. Right? Remember, lists order matters here. We know what's first, we know what's second, we know what's third. This is going to be super fast for us. So by exposing the position and letting the person interacting with our list have a position to interact with, they now get super fast speed to do any of these operations here. Now, going before and after is still going to be, they have to go find something. It might take them a little while to get there, but once they're there, it's super fast. So that's the idea with our positional list here. So let me open up PyCharm, and we'll do our positional doubly linked list, circular doubly linked list. It's a lot of fun. That's not what I wanted. I want the other project. Linked list, there we go. Excuse me. Okay, so we had a couple different versions here, but we got to our circular doubly linked list was the last one. So we're going to start, I'm going to keep this one here just so we can come back and reference this one later. Again, I'm doing more work than I need to because I'm copy pasting. We could like inherit from this and do all sorts of other fancy things. We're just not going to bother because I think that's probably more confusing, okay? Is that all right? So we want to be now a positional linked list. Now we're still circular, we're still doubly linked. I don't know if you really want to add all of that in here because that makes a really long name, but sure, why not? So positional, circular, doubly linked list. That's a fantastic name. I love long variable names or class names, right? It's very detailed. So we still have nodes to store our data, but now we also have a class for position, right? So we're going to write a class for position. The class for position needs to know a couple things here. Now this is where I'm probably just going to go, let me zoom in a little bit here for you, steal off the book here, because there's a bunch of things that position does that we need to know. So the position class needs to know who it belongs to. So it says, hey, I'm a position in this linked list. And we're going to use that because it's important as we're working with positions. They might have 3 or 4 or 5 or 6 different lists going on. And we don't want someone who gets confused, like, okay, I've got a list of courses you have to take, and I'm going to have a list of profs over here, and I'm going to have a list of students over here. We don't want those positions to get mixed up in the wrong list. And then you think you can add to a list, but it doesn't actually work like that. So we need to know what container we came from, and we need to know the node that this position references. So a position wraps around a node, because the node is our internal detail here. Yeah?
Are they also going to be connected to the one we did last class?
Yeah, the doubly links, so forward and backwards links, and there's the circular link there as well with the dummy node at the start.
With the dummy link?
Yeah, that just makes life easier for everything. So you don't have to have all the special handling cases. So it makes our code easier. Right? The book just uses header and trailer, and it's fine. He deals with the special cases. You can do that if you want. It's your code, right? So with this, then we need the container, right? Or I guess container's fine, and then we need to know the node. Right? So my self.container is the container, and my self.node is the node. Now, node we probably want to make private here, and container we probably want to make private. We probably don't want to give public access to these things. It doesn't matter super much here, but again, if we don't need to give direct access to these things, we shouldn't. That's fine. What we do want to have then is like, element, or I like data here. So to get the data, we're going to return self.node.data. So if you want to know what this position, what it's pointing at, right? So position is really just like, here's where you are in the line. Here's where you are in the list. It's pointing at one of those things. So if you want to know the data that it's pointing at, we can get it. Let's get the data back out. The book calls it element. We're calling it data. Is that okay if we use different names? That's not too confusing, hopefully. I'll put add notebook. Calls it element. I can do that, right? I can add comments. I try not to, but I can add comments. Right? So that's one thing we do. Another thing we can do is we can check, hey, are we equal? Are we the same position or not? Sure, we can do that. So it's probably just fine to copy paste this one here. Goodness, that's ugly. Oh, no, that was the comment. There we go. Okay. And I should add a note here from book. That's a good enough citation, right? We got that? It's close. All right. I'm not going to give you the page number because it's too much hassle right now. So this is equals here that took out the double underscore for me. So if the type of the other is the type of me, are we both a position class? This checks out what class are we, and then is the node underscore node the same as my node here? Do our nodes match? So do we both point at the same thing? Because it's possible we could get 2 different positions. So if you start at the front, so a person interacting with my list starts at the front and starts at the back, and they're going to use both of those and walk somewhere. Okay, hey, what comes after you? What comes before you? After you? Before you? After you? Before you? Eventually they'll meet in the middle. 2 different position variables really are equivalent at that point because they're pointing to the same node. So we need a way for the user to be able to tell, did I get to the same spot? Right? Because we can have duplicate data. They can't say, hey, is the data the same? Because we're allowed to store the same data more than once. We're not a set. We're not unique here. Right? So you can have Eric in your list 50 times. Like if you grew up with a bunch of Erics in your class, you'll have a bunch of Erics in class. Right? So we can't rely on the data. So the position itself can tell me, do I point to the same node? when I get there, so we can compare these things. And then for some reason they like the not equals here, and let's just return self equal other, and we want not is the cheating way here, because we already know how to define if we're equal. So if we're not equal, we've solved our not equal. Right? We don't need to do the same thing more than once. So it just uses the equals again, and we just do the opposite because we're not equals. So sort of cheating there, right? Not self equal other. I guess parentheses. I don't think that's necessary, but sure, why not? Let's go for it. Okay? So that's our position wrapper. That's what this does for us here, right? Node still does all the same thing node does, right? That one's all good. Now, we need to add a couple more methods. So we have our init method function here. So let's go add some of these other things, right? We said we were going to have a first and last. Give you the first position or give you the last position. So we're going to add a first here. This will return a position of the first node here. And then we also need a last. Now, we don't want to do the same things here, right? We want to kind of get rid of some of these functions here. Now, that's really the same as add last or add first, right? So I'm just going to rename it here. So instead of append, it'll be add last, right? Because that's what we're doing. We're adding to the end here. Insert, we're not going to do an insert at k, right? There is no insert of k in our positional list because we don't want them to do that. We want them to work with our positions, say, oh, hey, if you want to be the new index 7, go find index 7 and insert yourself before it, right? You'll become the new index 7, that sort of thing. We don't want them to work with those other options here. So we're going to get rid of this one. Now we're getting rid of, so front, yeah, we have first and last instead of front, that's fine. And we're not going to get an item at an index, and we're not going to pop items off here. All right. So adding last is fine, right? Adds in the node. For first and last, so when we work with positions, what we want to do is make a position. So if a lot of times we start with nodes and we want to turn them into positions, we know that'll be a function we're going to have to do more than once. We can make a little helper function for it. And they've got a really nice one here that says, hey, I'm going to make position. So this make position. So given a node, it will give you back a position that references that node, right? That's the idea here. So we're going to make a helper function here. So private make position given a node, right? So I give it a node that I'm looking at, it will give me a position back because I'm going to do that all of these things. When I want the first, I want the last, when I want what comes before, when I want what comes after, I'm going to be giving positions back to the calling code. So to make a position, I'm going to say, okay, let's make sure that I'm not the, in this case, the trailer or header, it's nothing, right? They use dummy nodes at the front and the back. We only need one dummy node because we're circular. So we're going to say, hey, if we're the dummy node, so if node is equal to self.dummy node, we're going to return none. This is an invalid position, right? So we'll see this later because our code will eventually, when you say, hey, what comes after you? And you say, what's after the last position? The next node, because it's a circle, is going to hit the dummy node. We don't want to give them a position that points at the dummy node. That's not a real node. That's just something we track internally. So we give them none. So when they ask for the next thing, we give them back, there's nothing left, right? So if it's not that, we're going to return self.position given self, right? Because we are the container. So position knows what container it belongs to, knows what list it's a part of. That's us.
What is self-position?
So that's the class definition. Because it's an inner class, we defined it as part of our class. It's self.position here.
Oh, does that have a class within a class?
Yeah. Yeah.
That's really... Is it common?
Sometimes. It kind of depends on what you're working with. So it may be common. It's not the tool for every job, but it's a good tool for certain jobs. Does that make sense? It's like inheritance. Like it's really handy when we want it, but not everything is inheritance, right? Not everything is that. Especially when you get to poker, people are like, "Oh, a hand is a card." And you're like, "No, that it's not. It's not an is a relationship. A hand is it has cards, right? So like once you learn inheritance, you're like, hey, everything could be inherited. No, it's not. It's not. So they say once you have a hammer, everything looks like a nail. Right? It's just a tool we can have, but we use the tool on the right thing. That's all. Yeah.
Why
So
want to hit everything? Right?
we do. We always want to hit everything. Yeah.
Do you play poker?
I'm sorry?
Do you play poker?
I have, not frequently. My brother was really good at poker. Did I tell the story about my brother? So he's 7 years older than I am, and he got into computers because my parents are geeks, and we always had a computer since I was a kid. So I got into computers because he was into computers and video games. Of course, I like video games. But he went off and got a computer science degree and then got a job, and he hated his job because it was awful. He worked in COBOL doing check processing for one of the payroll companies or something. And he's like, it's terribly dull, nothing's interesting. Sit around and like tweak a bunch of things all day long, and he hated it. So he quit that job and he played online poker for a living. This was back in the 2000s, I think, so early before online gambling was really a thing. Eventually that got shut down when everyone's like, oh wait, we should not let this be a thing because we haven't regulated it and we're not getting our cut, essentially. The states weren't getting any money out of it. The feds weren't getting any money out of it. So they cracked down on all the banks transferring money in and out to these places. They didn't make it illegal. They just said, banks, you can't do it. Whatever, nonsense. So he stopped doing that and went back to programming.
For a while, we make money?
Yeah, two or 3 years, I think, playing poker. So he would play 16 hands at a time. And he had a program that would bring the active hand to the front here. It was intense. Like, it was more work than it is to program because you had to like focus in. There was some German guy he found online that had a program that would track the stats. So everything gets logged. So it would parse all the logs to say, okay, this player, how often do they bet? How often do they call? How often do they fold with certain types of hands and things like that? So it would profile everyone he played with. So it would come up, hey, you're at a table with 10 players online. If you used the same account all the time, he'd have all sorts of info about you, which was fun. And then just knowing all the stats behind, hey, I should bet, I should fold, I should call, those sorts of things. So
he cracked the system.
I mean, it works because enough people who are bad at poker were playing online. It doesn't work if you play against other good people. It doesn't work out very well, but it's easy enough to take money from bad people, I think was the idea there.
Yeah, really lose money, right?
Yeah. So, but no, we would play for fun, and he would always beat me because he knew all the odds. Like, I can figure out some of the odds, but I don't have them all in my head. That was just too much brain power.
I like the game just for playing it.
Yeah.
Not for bag with that. Like,
No, yeah, it's a lot of fun. It's fun. So our final project will be based on Texas Hold'em, which is fun. So it's a poker variant. So it turns out you can calculate all sorts of odds and stats and things given any. So you could look it up in the database. That's the right thing to do, but we don't have a database. We don't know how to talk to databases yet. So we're just going to brute force it and figure out what the odds are for every single possible hand, and we can figure out whether or not we should play or not. And we can make a computer decide whether or not it should play or not, because it can figure out the odds as well, which is pretty fun.
right.
I got off on a tangent there, sorry. That's good. Yeah, poker's a lot of fun. So we'll make a position, right? We use the position class, we are the container, and here's the node it points at. So for first then, we're going to return self.makePosition of the self.dummy node.next. Right? They will always have a next. There will always be a node that's next. This will never be none. It could be dummy node itself. Remember, it points to itself and I'm empty. I don't care. If you ask for the first item and I'm empty, you're going to get back a none. Because when I look at dummy nodes next, that node is dummy node. I'm going to return a none position. There's nothing here. Right? If I have something, dummy nodes next is always the first thing. Easy. Same with the last, right? That's my make position given self.dummy node dot previous. The previous is always the last thing. If it's itself, I'm empty. Right? So because it's a circular list, this just works out really nice for us. Here. Code's super easy. Okay? So that's first and last, right? We did those ones. Now, after a position is a little bit trickier, right? What comes after or before a position? So if we are given a position, we need to get the node back out here. So again, we've got a helper function. We're going to be doing this a lot here. So they have this idea of validating. We said, let's make sure it's a valid position here, because you might give me a position from a different list, right? That's not a good thing. We don't want that. So we're going to make another helper function here for validate. validate position, given a position. I guess we can just call it validate maybe. I think that's what the book does, right? So the first thing we're going to do is make sure that it is a position, right? It's a position class. It's an instance of the position class. If you give me something else, it's not going to work here. So if it's not is instance of self.position, raise a type error, right? This is saying you're the wrong type. You're not actually my position class here. I don't know what you are, but you're not mine. I can't work with you. That's just a little bit of safety checking here, right? Then if it's not that, we'll see if it's not my container. If I'm not the list that this position is in, right? If I'm not your container, I can't figure out what's before or after you, right? I have no idea what that is. So then we're going to check if not self equal to position dot container, right?
What does it mean if not self?
We could say self not equal to, right? Or is not.
No, but what is like itself? What exactly is self?
Self is the list, right? Because this is a function in the positional circular doubly linked list class. So that's self. So self will be an instance of this list. So I could have 5 or 6 of these different lists out there when I'm using them, right? So whatever the list I'm working with is, if I say students is a positional circular doubly linked list, then students is the self, right? Because that's the instance of the list I'm calling my functions on.
Very quickly, how do you instantiate a class within a class?
Like we did with position, right? So self.position makes an instance of the position class.
Oh yeah, but outside of the bigger class.
So you probably wouldn't, right? So we would say this would be positional doubly linked list position, something or something. Doing that's going to be really weird because it needs a container. Like now we're getting into these details that I really don't know. So usually you don't mess with inner classes. They're like inner details for a reason. Right? Well, we can interact with them, but I don't call their init method very often. It gets to be a little weird.
What would the container be?
So the container would be the position or the list we made. So we could do it. It would just be really weird. And you also need a node, and we never give nodes. We never give someone direct access to a node. So they could go get it because you can go find these private attributes, but you shouldn't, because if you access the private things, your warranty is void. Right? You can't take your phone apart, otherwise your warranty is void. You can if you want to, but it might not work once you start doing that. Right? Once you start accessing the private attributes, it might not do what it's supposed to do. Same goes with Python. So make sure it's the right container. Then see what it is here. So there's a way you would mark the node to say it's no longer a valid node. So when we delete a node, one of the things we're going to do is set its next to none to say, hey, it doesn't belong anywhere here. So one last sanity check here as well. So then if my position dot node is none, raise a value error. Otherwise, then I'm going to return position dot node. Right, so all of this sanity checking will happen every time we're given a position, because I want to make sure it's a valid position that belongs in my list that I haven't tried to delete. Right? Valid position in my list, I haven't tried to delete. If it is, okay, good, now I have a node. So when I want the add after, given a position and some data, right? First I'm going to say my node. Right, so I'm going to get my node is equal to self.validate the position. Get the node out of the position, do all my sanity checks. Assuming it didn't raise an error, I can keep going. If it did, that's fine. I'm just going to puke on the user and make them fix it. Hey, here's a value error. You did a bad thing. You go fix it. Right? We don't have to do any handling here. We're just going to let that bubble up here and be thrown to the user or raised to the user. So they have to handle it. Otherwise, then, I'm going to add some data after this node. Now, if we're going to be adding pieces of data between positions or between nodes a lot, hey, yeah, it's a helper function. Thanks for suggesting that. You folks are on fire. Right? We're going to have a helper function. We're going to have a add between. What about betwixt? Is that fun? You can say betwixt. I don't know. Next node. right? Between probably makes more sense here, sorry. Between, it was just fun. So to add between two nodes, right? This is the code we had pulled out before, right? So we went back up here, right? To add something, we said, okay, where's our add? Make a new node. Here's next and previous. Tell my previous next that I'm next. Tell my next previous that I'm previous, right? Where we said, hey, thing that comes before me, I'm after you now. Hey, thing that comes after me, I'm before you now. I just jumped the line. Now I'm in the middle of the list, right? Good news. We let line jumpers happen with linked lists here. That's okay. It's not really a queue. You don't have to get in the back. You can jump the line sometimes. And people just smile and nod at you. Turns out, if you look young enough, you just say, oh, hey, I'm going up to my parents up later in the line. You can get through all the lines at Cedar Point really quick like that. You're like, oh, I'm just catching up to my family. And they're like, oh, yeah, there must be a kid catching up to their family. That's a pro tip for kids. All right. So to add between them, right? We said, okay, so I'm going to make a new node. So my new node will equal self.node given, oh, I need the data too, right? Add between, probably some data. We'll take the data. I guess this will be the previous node, right? We can even call it the previous node. Let's do next and previous. I don't know if it matters here, but just for fun, because that matches our other here. So then my next is, next node is equal to the next node. My previous node equals the previous node. Right? Make a new node, put it in between. So the new node knows where it goes. Now we need to tell its neighbors, hey, don't forget I'm between you now. So the new node's previous next is the new node, and the new node's next previous is the new node. Right? And then we're going to return new node. Okay? So it puts it between these two nodes. Right? So to add after, we get the node here. And then to add after here, we're just going to call self.add between. We're going to add the data between the node and the node's next. Node.next. Right? Because we want to go after this position. So we go after the node and its next. Right? And then we're done, and we're going to say new node, or we can do it all one line. I think that's what the book does. Return self.make position of a self.position. Oh, no, sorry. Make position of a self.add between. There we go. So call the add between, which returns a node, take that node, hand it to make position, and we give that position back. So when you call add after, you get the new position that points to the data you just added. Right? That's what this one does. So it'll say, hey, if I have 1, 2, 3, and I want to add after the number 2, let's add the number 27. We'll get 1, 2, 27, 3, and I'm going to give you back the position that points to 27. Right? So to add before,
1, 2, 27, 3.
If we added 27 in the middle. Right?
Oh, okay. Okay. So I think that's the order of the elements.
Yeah. Sorry, we've come up with better numbers here, but right. So to add before something, still we want to validate, but then what comes next is, I think we did this out of order here. We wanted the next node and the previous node. So to add after the next node, so next is this one and previous is this one. There we go, sorry. So this comes after, was it not previous? No, next node and previous node. Oops, previous node, next node. There we go. I was out of order. That would have been real bad. Gotta make sure we don't get those mixed up. So if we're gonna go before this node, right? My next node will be that node. Next node will be the node. And my previous node is the node's previous. Right? So come before this one. So that node will come after me, and I'll come after the one that's currently before it. Put myself in the middle. Right? And that takes care of those ones. So we can add before, we can add after any position with the same code. Because we always have a node there, because we're a doubly circular list, circular doubly linked list. There's always going to be that dummy node in the middle there for us. So always, we don't have to do any special casing, like, is this the header node or is this the trailer node? There's just always a node. Life is good. So we can add before, we can add after. Okay? First and last, before position.
Sure.
Yeah.
Do we need to code a list like that?
I'm sorry?
Are we need to code a list like that?
No, there's one in the library. We just do this for the exercise of understanding why it works the way that it does, so that you appreciate how pretty it is. That's why we write proofs in math. It's already been proved, right? We just write the proof ourselves, again, to hopefully understand it a little bit better. I don't know if that makes you feel any better, to feel like we're writing proofs, but we're kind of like writing a proof here. It's sort of what that's like, right? I kind of enjoyed proofs in math because I'm a little bit weird, but like I liked how they were like pretty. Like, look, I can prove this. I don't know. I thought that was really fun. So same idea. Like, I can prove this concept works. That's all. Okay, so we can add before, we can add after. And then what about getting the before and after? So to get before a position, same idea. We're going to validate the node. And then instead of make position, we're not making a new position. Or I'm sorry, we're not adding between. We're just going to return node.previous as a make position. Validate the position, get the node out, make a position of its previous link. Right? After is the same thing here. I can get the position that comes after a given position by the node.next. Validate the position, make sure it's valid, do all of our checks. It is a position, we're the container, we haven't tried to delete it, and then grab my next node and turn that into a position, give it back. So those ones are good so far. Add before, make position. The iterator we got to do in a minute. We'll come back to that one. Insert between. Yep, we can insert between. This is why I don't like all this superclass, subclass inheritance stuff. Like super insert between. Like we can just, I don't know. Let's just do it again here. Adding first, adding last. Okay, so we added first, right? We had a add last here. Ooh, we can make this a little bit cleaner here too. Add last then. Ooh, we need to increase our number here. So when we add between here, so this one, add between needs to make sure we're increasing our count, right? So self dot number of items plus 1 when we add between. That's important we do that. We would have had some bugs here, right? Our count would have been bad. Right, so adding to the last then, we don't need to do all of the same work here, right? We can just return self dot add, we want to make position out of self dot add between, given the data, the next node. So if we're adding the last, the next thing will be the dummy node, right? Because the last thing always points to the dummy node to complete the circle. The previous thing is what used to be the last thing. So the previous node then will be the self.dummy nodes previous, because dummy nodes previous always points to the last thing. So now we can do that with one line because we have these helper functions, right? I can add between things, I can make positions out of things. It gets a little long here, but that's how we add last, right? And then we're going to return that position. Adding the first is the same thing here. Why is this looks so weird here? Why is it like all extra highlighted? I don't know what's going on here. But we can add first. Oh my goodness. Self dot make position. We're going to return make position of self dot add between self and the data. There we go. So if we want to be the first thing, the next is the old first. So my next thing would be dummy nodes next. The previous is the dummy node, because the first thing points back to the dummy node to complete the circle. Right? So having the double links here is super handy. Self dot add between. There we go. Right? So adding first, adding last, super easy. We've got our helper functions. We say, hey, you go in between here. You go in between here. Right? So we can add first, we can add last, we can add before, we can add after. Now delete. Delete's a little tricky here. Let's do a delete. So if you want to delete a given position, we don't need to check for valid indexes either. So I want to define a delete given a position. So take this position out of the list here. So delete then, still we want to validate, we're a valid position, right? So our node will be self.validate, date the position. Why? I'm tabbed in funny here. What's going on with this? There it goes. Self wasn't purple before, now it's purple. Okay, so we validated the position. Now we want to take this node out. Right? To take the node out, we need to say, hey, thing that comes after me, skip me. Thing that comes before me, skip me. Right? So we had done before with our deletes. So node.next.previous, we're going to change the value to my previous. There's a lot. So drawing pictures of it can help. Right? When we had all the pictures, right? So say, hey, thing that comes after me, skip me. Right?
Like I'm saying to the next one to go to the previous one, to the one before me, is it?
So let me get a picture here. Right? So if we have a couple nodes, right? We had like 7 and 15 and 9. I don't know, right? And we got the little dummy node up here. So they all point to each other. So the next one, right, is that one. This one points here. 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 This one points here, right? We have a nice little circle. So I guess technically the first is 9. I drew it a little backwards. So we have 9, 15, 7, right? Because this is the next, this is the previous, and this one is the dummy node, right? So if we want to delete node 15, we have a position that points at 15. We say, okay, hey, the thing that comes after 15, which is 7, your new previous isn't me, jump over me, go to my previous. Hey, thing that comes before me, I don't come after you anymore. The thing that comes after me comes after you now, right? So we break those links. We say, hey, don't point here anymore, right? Take ourselves out of the list. Now we're still a circle, and we're gone. The last thing we do is we say node.next equals none. Right? This idea, this is what invalidates it. Marks as invalid. Right? That was what we were checking for when we were validating positions. We said, hey, it's a valid position if the node's next. Node.next. There we go, next. Is none. If the node's next is none, we've tried to delete it. This is our internal handling for I've marked this one as it no longer belongs here. So you might have deleted this position, but you could still have that position pointed to that node that's been deleted.
Because it's non, there's nothing pointing to it. Right?
Yeah. Yeah, so that marks it for deletion. So if they try and delete a position twice, it won't delete the second time. Nothing will happen. Because we've already said, hey, this node's been deleted when we validated it.
To be deleted.
Yep. Right? And then when we delete something, we need to take our self.number of items minus 1. Right? We took something out here. And then, yeah, that's about it. So that we can delete a node. Does it have a delete? Where's the delete node? I didn't know if we had one in here. I think it was from our parent class. Yeah, I think that's from the doubly linked. Again, these base classes are obnoxious sometimes. Right? So we can go all the way back up and see how that deletes if we wanted. Right? Where did that one go? Delete, which they got from, okay, so that one got it from the doubly linked base. Oh, that was the linked deck. Okay, it's doubly linked base. To delete a node. Predecessor and successor, is that better than first, previous, and next? Do you like his terms? The predecessor and the successor?
It's beautiful. Sophisticated.
It does sound more, I don't sound fancy enough, I think. I need to sound fancier so people think I'm smart.
Sounds like there's like a hierarchy going in the list.
Yeah. Oh, okay, it does return the data one last time, so we should return the data. That's the piece we're missing here. So we can set data is node.data, or we can just return it. We can return node.data. I think it was public, right? Data? Return the node data. We're good to go. Right? So we can delete a position out of our list. Right? I think that gave us all of the items here that we can do first, we can do last, we can do before, we can do after. Oh, the iterator. We left the iterator. Oh, replace. All right, we'll do replace, and then we'll do the iterator. So, yeah.
So how do we have it as like previous, next, and next, previous? Like are they like forward and back and forward?
So nodes next is the next node. That node has attributes for next and previous. So we're changing the next node's previous attribute.
But the previous attribute, isn't that the previous attribute for the next one? Isn't that the current one?
It points to, yeah, the value of it is the current node. So this previous currently has a value of our node, and we're saying change it to my previous to make me jump me out of the loop. So skip over me.
Yeah.
Yep. So the syntax gets really weird here. So it might be nicer to not do it in one line, right? We could say the next node is node.next, and then you could say next node dot previous equals the node dot previous. Right? Does 2 lines make more sense for that rather than 1 line? So we get the next node, and we change the next node's previous value. That makes it maybe a little bit more clear that we're changing a value of a node here, because now I've put a nice name to it. These entertain me, so I like writing these. I like all the dots, but it's a little silly here.
How do people create this kind of stack, like this kind of list?
So they would say, hey, I want here's my student list.
How
Students.
did they come up with that?
Oh, long time ago, people figured this out. Really smart people. They're like, how do I make it fast to insert things at a given spot? And someone's like, I know, we use positions. I don't know. It's been around forever. Not forever, but it's been around for a long time. Right? These sort of data structures. They're not new. They're not novel.
How much is a lot of time for them? Like 50 years?
Oh, I don't know. Let me see if we can Google that. When was a linked positional linked list invented? There's probably a research paper somewhere. Hans Peter Lund had an idea and published it in a paper, 1955. Alan Newell, Cliff Shaw, and Herbert Simon wrote it.
That was a long time ago.
That's a long time ago, right?
Computers? That's a long time.
Yeah. Oh, I didn't plug in. But that's how long this idea has been around. So a lot of things came from research papers, and still a lot of things come out of academic publishing, which is super cool. So someone's like, hey, I have an idea for something cool. Here's like sort of part of it here, and then someone will go and fully implement it here. So when was RSA encryption created? So RSA encryption is the foundation of how we have secure communication on the internet. This encryption protocol. In 1977, and that's actually their last names is why.
That's long.
Yeah, but the math has held out since then. Until quantum computing is a real thing, the math holds out. Once quantum computing actually catches on and people figure out how it works, this is null and void. No longer works. So.
I don't think, at least, that these super powerful computers, like quantum computers, should be available to anybody, like to a hacker, just to use them.
I don't know at what point in the future they become widely available.
Yeah.
I got no idea. People probably don't care about our secure internet traffic. Nation states probably care about our government's secure traffic. Right? And the working theory, if you ask cybersecurity professionals, go talk to some of the cyber profs, is that anything we do now can be decrypted in the future. And you can grab traffic online if you've got the right access and store it. So communications possibly could be being stored to be cracked in the future, decrypted in the future. I've got no clue. I don't know if people are doing it. I suspect they might be. I don't know. That sort of stuff is nuts. But yeah, so the math has held out since 1977. So this is a class of problem. Was it PNP problems? This one here. Polynomial time and non-deterministic polynomial time. Fun math stuff. I think you talk about this in discrete math. Eventually you get there, probably discrete 2 maybe. I think you talk more about these problems. But the idea is you can do P really quick, but to undo P, it takes a non-deterministic polynomial amount of time.
What is P? Is it an action?
So in our case, encrypting something, we can do like that. Finding the values we used to encrypt it, the NP problem, is ridiculously hard because we use prime numbers that are 2048-bit digits in length, right? Which is really big. So this, like, our key here, where's the cert? I want to look at the cert. So the cert here is, where is it here? It has something about it. Where is it? The key algorithm? Somewhere in here tells me the size of it. I don't remember where. Version, issuer, 384 maybe? So this one might only be 384. That's my guess here. I don't know. That's not the important piece here. So certificates can come in different lengths, and we keep extending the lengths as these things get easier to solve. What is 2 to the 2048? Power. So 616 digits worth of possible numbers, and we find 2 prime numbers in that range. Do some cool arithmetic, and we get RSA encryption. So to crack that, they have to find the right 2 numbers in that range, right?
Yeah.
Whatever, 616 digits combination 2 is really, really, really big. So that's why it's easy if you know the 2 numbers to solve P. If you don't know the 2 numbers, it's really hard to get the NP to reverse it. And that's why this is secure with our cryptography. That was a fun rabbit hole. This is really fun. I did an example of RSA encryption one time. It was really fun. You could do it in Python, actually, which is cool.
Like when you're encrypting, you already have the algorithm to do it, right? When you are trying to decrypt, you have to find the correct combination that matches every single encrypted character.
So this is a fun thing. This is worth the time. So with RSA encryption, this is a public key and private key pairing. So the idea is here, if I encrypt something with the public key, you can only decrypt it with the private key. If I encrypt it with the private key, you can only decrypt it with the public key.
What are these keys exactly?
Sets of prime numbers, essentially.
What?
Sets of prime numbers, essentially. So
are they like passwords?
not really, no. So the private key is 2 prime numbers. I know what those 2 are. The public key is a product of that. So we get the public key is P and Q, which gives me N. Something in here, and you do this, all this other fun stuff here, right? And then the public key, right, is our modulus N and the exponent E. The private key is D, P, Q, and whatever that thing is of N. Here. The math checks out. So if you have one, you can find the other. Or no, you can decrypt stuff encrypted with the other. So the idea with public key and private key encryption is that if you have the private key, you can assert you have access to this private certificate by encrypting something. So when you go to a website like wikipedia.org, it gives a certificate here, and it will send you something that's encrypted with the private wikipedia.org encryption key. You know that they have access to it because you can decrypt it with their public key. Public keys are listed publicly. There's like public list of public keys. That's how the internet trust works. So you don't know that they're actually wikipedia.org. You know that they have access to the private key of wikipedia.org. And you hope someone didn't get access to that. We keep pretty tight control over keys because otherwise bad stuff happens. So then you can initiate, once you know that they have access to it, you initiate secure connection by using the public key to encrypt something that only they can, or only someone with access to that key can decrypt. So you establish a synchronous encryption scheme that you're going to use. So this is asynchronous encryption is the public key and private key, the pairings, which is slow. There's a lot of math that has to happen here. So we use it to set up synchronous encryption communication, which is much faster. And you do it every time we have a new connection, you come up with a new synchronous key, essentially.
Okay.
And those keys are also hard to crack. But you can communicate the same key back and forth to each other. You both use the same key. Works out nice.
Crazy. What language is that programming?
Not sure. All right. You can do it in whatever you want to use for internet communication. You'd have to figure that out with. Yeah, this one's fun. So you can do these sorts of things here with all that issue. Yeah. All right, so we were doing the nodes. We deleted a node. We needed to, the last thing we were going to do then, right, was the iterator. The iterator is actually really cool. So the idea of how can I say, for item in this collection, do something here. So to do an iterator ourselves, we're going to keep track of, where we currently are. So I'm going to just steal his code shamelessly here. So we can define an iterator function, iter function. And we're going to use a new keyword we've never seen before. So we're going to say, okay, start at the first. So my cursor, I don't know, I like current equals self.first. Okay, I'm here. Now, while it's not none, right? So we're gonna say while my current is not none, because eventually when I hit that dummy node, I'll get back a none, right? As I walk this, I can say, hey, what comes after, 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 other direction, until we're done. So as long as it's not none, I can go and yield my element, which is a position. So yield is a special keyword here, which is really fun. So we're gonna say yield current dot element. Or no, dot data, right? I think we called it data. Current data. Yield that the data pointed to by this position. What yield does is it says, give it back and then wait. So the code kind of like pauses here and it kind of leaves it on ice, which is a little crazy with how this all works. But it says, okay, just hang on. When they ask for the next thing, now I'm going to go current, current is going to equal self dot after current. Right, go to the next one. So the yield keyword actually sits, pauses, and waits. So if I do a loop, so for item in this collection of students, I'll get the first one, do something with it. The loop will come back and say, okay, give me the next one. Iterate to the next one. Now my code keeps on running. So it sits here and waits. It doesn't continue running. It just pauses itself mid-run here. So this gets a little weird on our when we try to like figure out where we are in the stack, which is fun. So now we can iterate over. So if I make a collection, right, maybe we have students, is a positional doubly linked list here. Right, and then I want students.add first. Let's add Eric. And students.add last. We'll add Jeb here. And students.add last. We'll add, was it David? Sure, we'll add David. So now I can say for student in students. Because I wrote the iterator, I can print the student. Right? So I'm going to pause here with my breakpoint here. So let's run this in debug mode. We haven't actually written any code that runs yet. I don't want that one here. What was that? Let's continue. Oh, invalid syntax. Uh-oh. Okay. Our define first is invalid. Are we like, is the tabbing off here? This is super weird. What is, yeah, the tabbing's off here, right? That one, that one, that one. No? It all looks fine. Define and add first. Why is this all like highlighted? I don't know what I did here. Let's tab it back and tab it in. Tab it back, tab it in. I don't know, let's try that and see if it'll run now. Nope. Invalid syntax. Oh, I think my return lines, because I didn't add my backslashes. Was that it? Is that what I needed? Is that why? No? Invalid syntax.
Like an indentation thing?
Yeah, there's usually the indentation's bad. I think it's fine. What am I missing
Why don't
here?
you go back to the, did you add the previous line correctly?
Yeah, okay, the line before it. Yeah, let's see. Let's see. So that would be the add last one here. Oh, yep. Missing a parenthesis. All right. There we go. Thank you. That's right. It errored on the line before. All right. Okay, we're close. We're close. So we've got an unexpected keyword argument next node. So making a node then, we said apparently wasn't next node. What is our node? It just wants next and previous. Okay, I named those badly here. So that's just next and previous. So is that it for make node? Okay, let's try that for add between. All right. If not is instance self position. Oh, if position. Type of position? Nope. Hang on, we gotta copy that one better. When it was validating. Not is, oh, P and self position. There we go, the position. Position. So the is instance is similar to like when we did the type. We said, hey, is the type equal to the type? Where was that? In our type of other equals type of self. It's like, is it an instance of this position class? Is its type that? It's slightly different. For our purposes, it does the same thing. Right? Okay. We're getting there.
What is is instance checking for?
Seeing if position is an instance of this class. So is the type of this class the type of this position? So we can't use type here because we can say type of self to get my current back, and we can get the type of the other to get theirs back. But there's only one type here, right?
Yeah.
So I can't say type of self because I'm not a position. So we use the is instance here, but doing like the same sort of checking. Hey, it worked. All right, now we got to debug. We finally got through. Okay, so now we got our students collection here, right? It knows nodes, it knows positions, it has attributes, these sorts of things. It doesn't look really pretty when we start trying to debug it here, because I can see, hey, dummy node, I can see dummy nodes next, I can see next, I can see the next, I can see the next. I'm sorry?
It goes infinitely.
Yeah, because next is the dummy node, and then that one has a next, which is Eric again. So as many of these as want to open up, we can just keep on, like, it will just keep going in the circle here. The debugger doesn't know we hit the start of the circle.
Will it keep going infinitely? Really?
The debugger will, yeah. So I can just keep opening these as much as I want. I mean, we could do it until we're bored. I think we're bored talking about RSA already, so maybe we'll stop here. But yeah, so you can look at it that way, but it's a little tough. So what I want to do then, right, I'm going to say, okay, for each student in students, I want to step into my code here. We're going into the iterator function. So the iterator function says, okay, get the first node. While it's not none, yield. Now you notice it's not on the call stack. There's no, like, we're not waiting for a function call to resolve, but somewhere behind the scenes it's holding on. So I don't know if this is actually multi-threading. I should look that up here or not, but somewhere it's tracking this that's not our call stack, which is sort of neat. It's a little bit magical right now with that yield keyword. Right? Then I'll print the student, and I want to step into. So now when I step into, now it goes right back to where it left off and says, okay, the next thing I do after the yield keyword. They wanted the next one, now keep running.
But is there like an internal stack that we don't have access to?
I think it's multi-threaded. I think it's Python yield multi-threaded or something like that. I don't know. Oh, it doesn't? So it tracks it. The global interpreter lock, maybe? Thread yield, I'm not entirely sure. How does Python yield work? Let's see. What does it do? How to use it? Yield keyword, how to use it, understanding it.
Shall we ask ChatGPT?
We should. GPT. Let's do it. How does the yield function work in Python? Why is it not on the call stack? Or something like that, right? We'll see if it knows what we're doing. That's so cool, it keeps all your history. It's also a little scary, but really cool. I think there's a way to clear that.
Can't you delete it?
I think so. I've not tried. It's handy sometimes. I was like, oh yeah, how does this all work? We broke it.
Yeah.
It's yielding.
So let me show you.
Yeah. All right, we'll see if that one comes back later. But yeah, so that's what that one does for us. So that's the iterator function. Oh, it's almost there. Did it stop? There. Okay, a generator function, suspended state, so it can be resumed later. It has an execution state, returns a generator object, which maintains the state of the function here. So what's actually returned then, it knows where to go back to. So it's not a separate call, but it holds that separate call. I think that sort of makes sense. We need an extension cord so you can charge up front here. I used to have a 10-foot one I would bring, but my backpack got heavy. Okay, so it will hold on to the next thing. It remembers its state. That's kind of fun. Does that make any sense? So it's like, it's a wrapper around it.
Kind of is.
Cool. All right, so that is it for our positional linked list. And that ends the chapter. I think that was it, right? Our sorting, we're not going to get to sorting right now. That's fine. We don't need to do our sorted list. Linked list versus array-based sequences. So that's the last piece. So it's timing-wise, right? We said all of these things are instant now, right? Deleting, no matter how many items I have in the list, is O of 1. Because I just say, hey, take me out of the list. Doesn't matter if I've got 1,000,000 things or 5 things, same amount of time. Adding to the first, O of 1. Adding to the last, O of 1. Getting the length, O of 1. Iterating. That one's not O of 1 because that's every n item. I think that makes sense. Anytime you iterate, it's n items here. Adding before, O of 1. Adding after, O of 1. Getting the next one, O of 1. Getting the before one, O of 1. Getting the last one, O of 1. Getting the first one, O of 1. Right? All of those are O of 1, but now the problem is I don't have a function for add at index 37. The only way you can do that is if you're counting the indexes and say, hey, okay, after. So we make the caller do that work if that's what they want to do. We don't have a function for it anymore. So all of our functions are super fast, but if you had 1,000,000 things and you want to get to item 500,000, you've got to call 500,000 times next, and over and over and over again. So someone using a positional list can do all sorts of cool things. They can track different positions. So if they want to speed things up and say, hey, I want at most to have to go like 15 items up and down a list here. Every 15 items, they can track another position, and they could have a list of positions if they wanted. Hey, here's position index 10, here's position index 20, here's position index 30. They could do that, and they could add and subtract from between them here. Now, as soon as you add something, though, they're no longer at that index anymore. It has its own issues. But we're giving the flexibility to whoever wants to use my list here. Right? So that we'll say, hey, this is the Eric position, add first, and this is the Jeb position, and the David position. Right, so any of these things I can say, hey, students dot add after or add before. So if you wanted to add before the David position, so I'm going to say before the David position, I want to add in John. Right? These other positions are still all valid here, and this will be the John position. Right?
So theoretically, John will be before Eric and after David.
So Eric's first, then Jeb, then David. So John's going to go between Jeb and David because we're adding it before David.
Oh, before David.
Yep. So if you want to hold on to all your different positions, you can. It's whoever wants to use your code. I could have 50 positions for 50 items. I could have 50 positions for 5,000,000 items. It's up to whoever's using our linked list to determine how they want to do that there. Right?
Well, how does the list resize itself?
Does what?
Does the list resize?
No, so there's no resizing because we're not an array. There's no contiguous block of memory we need to get itself by index. When we make a new node, we just say, hey, Python, give me some space to store this in memory. And Python asks their operating system, give me a memory address. And now it stores that location. So the only way to get there is you have to follow the trail because you don't know where it is in memory. So it's over here in memory, and then it's over here in memory, and it's over here in memory. We don't care. We just say, okay, go read whatever's there. Whatever memory the operating system gave us, go read it. But it's not in one big block.
What if you create a loop and 10,000,000
Sure.
items?
Yep. So we'd have 10,000,000 items in our linked list. Right? We can do that. So let's take out my breakpoint here. So for in range 10,000,000. Right, like we did with our performance testing, right? So let's make a new. So here's a numbers is a positional. You want to add first, add last. Does it really matter? We'll just add last.
Yeah.
So now we'll get 0 to 9999999, right? So this will be really fast. It's done. Oh, not quite. Sorry, still going. Should be done any second now. Should be. 10,000,000 shouldn't be that slow. There it goes. So, what, 7, 8 seconds or so? Did it count? Did it track that? I don't think it tracked it. How many seconds that was? We can do the timing to add 10,000,000 items. It'll do it. I'm sorry?
Do you want me to time it?
No, I mean, it doesn't. So the other fun thing, right, they don't take up a lot of space, but you can see it uses up memory here. So let's go run this here. And I'll see, eventually, I think I've got a Python in here somewhere. Let's go by memory.
PyCharm?
Yeah, PyCharm. We can see it's, nope, not Edge. Oh, it stopped. Where'd it go? I had it. Oh, it already finished. So let me try it one more time, see if I can catch it. PyCharm, using more memory, using more memory, using more memory, using more memory, using more memory. Because I'm storing 10 million numbers now, right? And for every number, you have to store the address of what comes before it, the address of what comes after it, and the position. It's like, there's a lot of overhead to use a linked list. Because to store one number, I need the before, I need the after, and I need the number. So like 3 times as many pieces of information I have to store, and I need the node, right? Versus the array is just, here's a contiguous block of memory, we're done. So, yeah, they're fun. All right, we good? Awesome, so don't forget, we've got checkers coming up here. That is due on the 20th, so on Tuesday. So we'll have Lab Tuesday, we'll do some stuff with linked lists. There's not actually a lot to do with linked lists. Won't be a very big lab, kind of boring. Because we've looked at the book, we've done it up here, we'll play with them. That's it. It's, just practice using them a little bit. But then checkers, 2 p.m., I'll go over the checkers solution. Okay, and then we'll talk about project 2 after that. Right, and we'll keep on cruising. We good? All right, see you folks on Tuesday then. Stay warm.